into the stationary phase better than either the protonated form or the totally unprotonated form, because they both have charges. One has a plus charge, the other has a minus charge. So the zwitterion, being electrically neutral, it's a dipole, but its net electric charge is 0, actually will extract better into the stationary phase. So there is a pH at which it has maximum retention. Now keep in mind that the compounds in your mixture that don't ionize, they don't change retention as you change pH. So let me just plot some neutral compound on this curve. You know, it could be flat and up here, it could be flat and down there, it could be flat and down there. But clearly, in this case, you've got at least 2 pHs where the separation is going to be quite difficult. So, just because the compound you're interested in is neutral doesn't mean you can ignore pH effects if there is stuff in your unknown that's ionic, because you might pick a pH where the ionic and the compound you're after coalesce. Now you can think of this as an evil. You can also think of it as job security, because engineers don't understand this at all. Physicists certainly don't understand what's going on here. Chemists, this is mother's milk. Okay, I could go on and on and on about pH effects. This gives you some idea of what you got to deal with. Now, what I call additive effects applies to species that we add at low concentration, typically to interact only with some of the molecules in the sample. Here's a nice chromatogram illustrating why we might add an additive. This is the chromatography of a bunch of catechol-amine derivatives. Catecholamines are one of the classic neurotransmitter type molecules. This is I forget which of the catecholamines this is, but it's a simple one. It's very easy to reduce this compound. It's electroactive. It's part of the charge transport system in neurons. These is a family of these catecholamines. This is the retention you'll see in essentially 100% water. They're essentially unretained. If you add organic mobile phase, the retention is going to even go down a little. There's not much you can do. You can change the pH and screw around, but you're not going to get these compounds to be retained. So what some clever people did is you can set the pH properly and you can get a positive charge on that. Now normally that would decrease your retention even more, which is not what you want. I'll stop in a minute. I'm right in the middle of this stuff. If we add a compound like an octyl sulfate, that's a CA chain with an SO3 minus on it, to the mobile phase, what's going to happen is that in the mobile phase, you're going to form ion pairs between your catecholamines and this stuff. You're essentially derivatizing, if you will, the catecholamine with this long hydrocarbon chain. and you're canceling out its positive charge. Well, canceling out the positive charge is going to increase retention, and adding a long hydrocarbon is going to increase retention, and it only takes 3 millimolar of the octyl sulfate to turn things around and give you a beautiful chromatogram. Here are those compounds that were in the previous chromatogram, and here's the effect of the concentration of butyl sulfate on their retention. And you can see, this is a pretty good effect on retention. But butyl sulfate is a short chain. If you want more retention, you go to a longer and longer and longer and longer chain. So here's decyl sulfate, C10. Now let's just check the scale here. That's 2. That's 25. A lot more retention. But we're beginning to see some evil. It goes up, you add even more decyl sulfate and the retention starts back down again. Here's, I forget what the compound is. We took one of those compounds and we're looking at the effect of butyl, hexyl, octyl, and decyl sulfate. And these are all curving, but this one doesn't come down. This one might be coming down a little. This one might be coming down a little, but this one, there's no denying it's coming back down. It turns out that this concentration right here of the sulfate for the decyl is its critical micelle concentration. What that means is the concentration of the decyl sulfate at 20 millimolar is so concentrated that there's a change from where this stuff is a monomer to where it forms large aggregates called micelles, otherwise known as a detergent, otherwise known as soap. And so it forms these aggregates, and the interior of the aggregate is very hydrophobic, and your solute molecule decides it's going to like the interior of the micelle. And now, we had it going into the stationary phase, but now we're forming a stationary phase, something chemically like the stationary phase, but it's in the mobile phase. So that the poor analyte now has to decide, am I going to go out of the real mobile phase into the real stationary phase, or am I going to go out of the mobile phase into the pseudo-mobile phase, which is the micellar phase that's being pumped through the column now. And as you increase the concentration, there are more and more and more micelles, and retention shifts into the moving mobile phase. And of course, the stuff comes out of the column earlier. I don't want you to believe that micelles look like this. This is some artist's rendering of what he thinks it looks like. I don't know what he was on at the time he drew this. This is a lot better depiction of what a micelle looks like. It looks like a ball of snakes. It is not highly ordered at all. The solute might decide to sit down in there, or it might decide to sit out in what we call the polar head group region. Either way, it's in the micelle and it's going to come out of the column quicker. Okay, this is an important part of how people adjust selectivity and retention in reverse phase chromatography. It is tremendously important in capillary electrophoresis. And we'll have to come back to this later. But this is the basic chemistry. Alrighty, we'll see you Monday.